Hello and welcome to this tutorial on binaural audio processing using Python. So in this video, we're going to learn how to use HRTFs or HRIRs taken from publicly available datasets to binauralize or spatialize sound, which is mono or stereo, into binaural format. So binaural audio will provide a spatial sound impression when you listen on headphones. So for this video, and for running this demo, you will need to listen to the sound on headphones. Now, this video is going to be divided into two parts. In part one, we're going to look at the basic steps of HRIR processing. We're going to choose some sets, visualize the data, choose example sources to spatialize, check channels and sample rates, convolve the HRIRs with the example sources, possibly add them together and normalize or scale the loudness, and create then a 3D audio mix for headphones. So starting from mono sources, after convolutions, we'll have a bunch of stereo sources, which are binauralized. We add them together, and we're left with a binaural mix. In part two, which is going to be another video, we're going to see at randomized sound field displays, multi-source binaural displays, using SOFA files, which are particular formats for HRTF data. I'm also going to talk about libraries and dependencies needed to run this file, publicly available HRIR and HRTF sets, and the file structure that I set up in order to run this demo. The file itself and the original source material will at some point be available, and I will add the links down to the description of this video. We're now going to cover equalization filters for headphones, although they're very important, but they are beyond the scope of this tutorial. Now, before we start, we need to make sure to have some of these libraries installed. So these are non-standard Python libraries, so they do not come by default in your installation. So to get those, what you'd need to do is open the Anaconda prompt and type pip install and then the name of the library. So for example, Librosa. I already have this installed, so I do not need to do this. But in case you run into problems using this first block, then have a look if you have those installed. The other thing to look at here is how I have structured my work environment. So this is my parent folder where I have the script running from. I have here a folder called samples 48K. This is where I keep all my source material. These are all ambient sounds. And then I have my HRTF sets already pre-downloaded and organized in this folder. So this script assumes that you have a folder for HRTFs and a folder for source material. Before moving on to the code, I wanted to cover the HRTF sets that I'm going to use in this demo. There are plenty of publicly available HRTF sets. Here I compiled a list with some of the most popular ones, and I divided them by format. Some of them provide math files, which you can use in MATLAB. Some of them provide WAV files, which you can use pretty much in any software. And some of them provide SOFA files, which is the spherical oriented format for acoustics. And those are a little newer in the scene. So in part one, I'm going to use two of the wav-formatted datasets. One by HRCam called Listen, and one by MIT called the KeyMart dataset. I'm also in part two going to use a SOFA database called the spherical far field. Now, to get hold of this data, you have to go to their specific web pages. So this is how the HRCam Listen web page looks like. And here you can download files that belong to particular subjects that have been measured individually. when you download those files, they look something like this. This is a bunch of files for the same subject at a fixed radius at different theta angles, which is the azimuth, and phi angles, which is the elevation. So here you can see how many measurements are there in this dataset for each of these particular individuals. And we have a full 360 sphere of angles. Now it's important to make sure that you know how a dataset is formatted and what angles it does provide, because that is going to affect how we retrieve these angles and how we choose the HRTF that we want. For the other dataset, the KEMAR MIT dataset, you can download it from this page, and you can download, for example, something called diffuse, which is diffuse field equalized HRTFs. They probably sound a little better than those that are not diffuse field equalized. Now, in terms of files, the MIT dataset comes with subfolders divided by elevation grade. If we look at one of them, for example, elevation 0, we can see that it contains azimuth going from 0 all the way to 180. So this is half of a circle. And to retrieve the other half of a circle, in this case, we assume symmetry. So by exchanging the left and right channels in each of these angles, we obtain the corresponding channel, the corresponding position on the other side of the hemisphere. So sometimes they come like this, just covering half a circle around the head. Later on in part 2, we're going to look at SOFA files. There are plenty of HRTF and HRIR datasets on Zenodo. And here we find some of those SOFA files that we're going to see in part 2. And when we look at the SOFA files, they are more compact. So each one of these files is a full dataset. And all the information, all the angles, elevation, azimuth, recordings are all inside the SOFA files. Other HRTF datasets that are worth to mention are the SADI dataset by the University of York. This one provides head scan data and all the HRIRs available both in SOFA format and WAV format, with and without reverberation. The other famous one is SIPIC, which has been used many times in 3D audio and is by UC Davis. And this one also provides tons of angles measured on a lot of people with annexed anthropomorphic data. Now let me just show again how I organize all these files. So in my parent folder here, I have a folder called HRTF sets. And inside here, I put my listen data, MIT data, my SOFA data that we're going to use for these tutorials. And some of those have a subfolder structure, so you need to kind of keep in mind that there are some subpaths and some choices to make. For example, we could use the raw HRTF recordings or compensated. Usually compensated are equalized, so probably sound a little better. And we have different formats available. We're going to use WAV files in this tutorial. Here we are. Okay, so digging into the code, we can start by running this portion of the code, which includes all the libraries that we're going to use. Now, besides the standard libraries, we're going to use this one sound file to read audio, SOFA to read the SOFA HRTFs in part 2, librosa because I like the resample function that they have and makes certain steps more convenient. We're going to import signal from SciPy because it has a fast convolution function. And then we're going to import IPython display, the audio function from IPython display for listening audio within the notebook. Okay, so now I have computed this, and let's move on to the next step. So here I'm specifying the directories where I'm storing all this data. So this is specific for my computer. So if you're using a different data structure, you might have to check those again. But here I'm defining a source directory for my sound samples and source and directories for my HRTFs, the MIT dataset, the listen dataset, and the SOFA dataset. And I'm pointing directly to the folder that contains either WAV files of the HRTFs or the SOFA files. I am parsing the contents here so that I can create lists that are easily accessible, and then I can see what I have inside of it. So here, let's see what are my sources. I have a whole list of file sources that we can specialize. Those are all ambience sound, cars, traffic, motorcycles, some construction sounds, some animal sounds, barking dogs, some baby sounds and children, some crowd sounds, some car sounds. So this is the material that I'm going to use, and I'm going to treat some of these as objects that I'm going to specialize in my static display. So let's start with part one. We're going to virtualize one single source, and in this case, let's start with the MIT set. We're going to use time domain convolution for this basic example, and then later on we're going to do something different. So here is my MIT folder. Just for convenience, I'm just printing out here what are my available angles. And now I can use the index of each one of these strings to point to a particular HRTF. So in this case, I'm just putting a random position, and I'm using this to load the HRTF using sf.read from sound file. Now the output to this will give me an HRIR, which I expect to be 2 channels, and a sample rate. I'm going to print this. So here we go. We are using the HRTF at the azimuth position 125. I fixed the elevation at 0. So here, if we go back up, you can see that I chose elevation 0 just to keep it simple. And we see that the sample rate is 44,100. The data dimensions is 128 samples by 2 channels. Now we can also listen to this. We can listen to the HRIR, and we should be able to hear a little click. Now this click that you hear is the input response itself, and you should hear this coming from a particular direction in space, as the HRIR itself has spatial information in it. Now to play using the audio function, you might have to transpose if it's a stereo file, because this audio function wants to read stereo data as 2 rows, and here we loaded it in as 2 columns. So there's sometimes some different formatting differences between different functions, and we can use dot transpose just to simply switch the columns with the rows and make it be readable by our current function. Now in this next cell, we're going to visualize how the HRIR looks in time domain. And we do this by plotting each channel in time domain and just observing what the graph looks like. So we always expect the left channel to be the first column or the first row of our HRIR data, and the right channel to be the second row. So in Python we start from 0, so the first row, the first column is this one, and the second column it is at index 1. And now what we see on this plot is that we have the right side, which is the second channel, arriving earlier than the left side and also having higher energy. Now this is expected because we chose an angle of 125 degrees. So using our clockwise convention, 125 is on the rear right side. So we kind of expect this kind of behavior. We can also visualize the same data in frequency domain, and this is effectively the change between HRIR and HRTF. So now in HRTF, we can see how the behavior changes across frequency. And as expected, the right channel has more energy than the left channel in general. We can also see some particular changes in position of the peak and notches. Those have to do with the particular region that we're looking at. So here, this plot looks at the magnitude of the HRTF, and the HRTF itself is a Fourier transform of the HRIR, and it's another way to look at the information that we have. So the next thing we're going to do is loading an audio source, and we can choose any source from the list of ambient sources that I showed earlier. And let's see how it looks like. So first thing that we see is the sample rate is 48K. Again, I'm using SF.read, using my source index that belongs to this particular source, floor nail, and then retrieving the sample rate as well. We can see the sample rate is different than the sample rate of the HRIR. So this means that we might have to do some resampling. And the other thing that we see is the dimensionality. This is stereo. So because of the two channels here, this is the number of samples. And we do not really want to use stereo in this case because we want to just treat my source object as a monofile, like a spatialize with the HRTF pair convolution. So there's no need for this to be stereo. So what I do is I'll collapse this file into mono. So to do that, I'm checking on the shape of the signal, and I'm checking the second dimension of the shape, basically this number. So if this number is bigger than 1, then we have stereo, and we make a mono version by taking the mean of the two channels sample by sample. And now we have a mono signal. So let's play the file. So this is the original file before any spatialization has been applied. So as said earlier, the sample rates of our source file and the sample rate of our HRIR file are mismatching. So here I have a quick function that resamples the one or the other file according to what is the higher sample rate. So in this case, I'm feeding to this function the source file and its sample rate, the HRIR file and its sample rate, and I should get back the same signals with a new sample rate, which is the biggest one among these two. To resample, I can use librosa.core to resample, which takes a file, target frequencies and its own starting frequency, and it needs the file to be transposed because it reads stereo sounds as rows, not as columns. But that's not a problem because then we retranspose back to what we wanted. So using this function, here we have resampling, and now everything is a 48K. And we check the dimensions again just to be sure. So we have one mono source file, which is what we're starting with, and we have one HRIR with two channels. Now because we resampled the higher rate, we have a few more samples than what we had before. I think we had 128 before. Yes, now at the higher sample rate we have more samples, and we have 140. Okay, so now that we have a matching sample rates, it's time to do the convolution. So this is the real key part of spatialization. So we have a time domain convolution here, between our mono source, the left channel of the HRIR, and the right channel of the HRIR. So here I'm convolving one channel at a time and storing the result into these new variables, SL and SR. Now, once I have that output, I can put it together in a new stereo file, which is two channels, the left and right channels, coming from those convolutions. And this will be one single data structure that represents my stereo file with the two columns stacked together. So I'm going to run this, and this is my output. So my final data dimensions here are this amount of samples, which is a function of how many samples we started with, how many samples the HRTF is long, -1, so this is the exact number that we have down here, and two channels, right? So we expect this to be two channels because we need to feed the left and the right side of the headphone. Now we can listen to this, and we expect those hammer sounds to be spatialized now. So hopefully you heard this coming from your rear right side. If not, then make sure that you have stereo headphones plugged in and try to listen again. Finally, we can save this file. So we're using sf.write. Make sure all these transpositions are correct. I have to transpose again for the audio file, but not transposing for the save file. It depends which library you're using at each point. You might have to move these things around a little bit. And that's it. We have our file we can listen outside of Python. Now for this next exercise, I'm going to add a little bit of variation as I will virtualize two sources instead of one, and I'm going to use the listen dataset instead of the MIT dataset. Now those two sources will be mixed into the same binaural output, so we're still are going to end up with a two channels binaural mix for headphones. I'm also going to use frequency domain multiplication, aka fast convolution, instead of time domain convolution, simply because it's a faster way to obtain the same thing. Now, as the first thing, I'm going to explore the listen dataset and see what I have. Here, these are all paths to my HRIR files. So these are my folder structure. You can see that I'm using a listen dataset. This is a particular measurement performed on subject IRC 1025. These measurements are compensated, so they're equalized, they sound a little better. They're in wave format, and so on. So when you look at the file name itself, you have radius information, so distance, and each file has the same distance, which I suppose is 2 meters. Then you have azimuth information, starting with T, which stands for theta, and then elevation information starting with P, which stands for Phi, the Greek letter. So we have a full 360 circle here, but it always helps to look at their documentation page. So this is the dataset download page, and you can see here a little bit more information on what exactly is there. So we have azimuth in degrees going from 0 to 180 for sources on your left. Now this is an anti-clockwise convention, which is the opposite of what we used before. And it shows that there's a little bit of difference among data sets, whether they're produced in Europe or America, different universities, different laboratories have been using different conventions. And it's always important that you can keep track of this from the documentation page. Elevation, it goes in 360 with 0 for sources in front of your head, high numbers for sources below your head, and these lower numbers for sources above your head. So that's pretty straightforward. So we just need to remember that we need to invert the left and the right hemispheres from the clockwise to anti-clockwise convention when we use this dataset. So here what I'm doing is I'm choosing two of these at random, and then I'm loading them using librosa.load instead of sf.read. Now I'm using librosa first of all for adding a little bit of change to the code, but also because it allows me to resample the HRIR immediately instead of having to check and using a resample function. And I also can have the option to collapse to mono, which I do not want to do because this being HRIR stereo data, I want to keep the left and the right channel separated so that I can have independent information for those two channels. The thing to keep in mind is that librosa loads a stereo file in the opposite way of sf.read, so our columns will be rows and our rows will be columns, and we're going to check on that. So let's run this code. And now here we can see that the random selection fell on an angle at 270, so being this anti-clockwise, this means straight on the right, and 180 means on the back for the other direction. And my dimensionality here is that my channels are organized as rows instead of columns. So earlier on, we had n rows for 2 columns in the previous example using sf.read, but here we have 2 rows per n columns. So this does not really matter as long as you keep track of it. And it's only a matter of transposing, so switching the rows with the columns when you need to use the data across different functions and libraries. But it's important that you know what you're dealing with, how your data is organized. Otherwise, if you don't know that, you might be feeding rows instead of columns in certain instances, and that can create problems in your computation. Finally, I'm also printing the sample rate, which is defined here as 48K, so naturally it will be 48K when we go back to read it. Now, the only thing I'm going to change is that I want to maximize the perception of 2 sources being separated in space. So instead of choosing a random selection of positions, I'm going to use some predefined positions that will maximize this spatial separation in my binaural mix. So here I have an angle 30 degrees, so in this case will be front left, at 240 degrees, which in this case will be back right, both at 0 elevation. We can listen to these examples and keep in mind that you do not need to transpose if your audio is already organized as rows. Your channels are already organized as rows. So we do not need to transpose in the audio function. So now we should be here a click on the front left. I played it a few times, and one on the back right. There you go. And again, you need to have headphones for the spatial effect. Okay, now that we have our HRIR files, we can visualize this just for the sake of understanding how they look like and whether everything is okay. So here I'm taking the frequency domain. Remember to make sure you always get the axis right. So this has to do also with the way it's structured, whether these are whether your channels are columns or rows. You need to change this axis information accordingly, otherwise you take the FFT in the wrong direction. Here we do all that is necessary to just extract the magnitude out of the NFFT. And we can just go straight to visualization right below. So here we go. These are my 2 angles, both at 0 elevation. One is at 30 degrees, which in this case is front left. And we do see higher energy on the left signal, the ITD and the IID, they're both in favor of the left side. And you also see like the energy across frequencies being higher on the left side. Conversely, for the other position at 240 degrees azimuth degrees, meaning the rear right, we see that the energy is more present on the right channel. And here we have the right signal showing more energy than the left. You can plot these pretty much straight away. You have to use transpose to use PLT to plot in time domain in this case. So this is just to say some functions take columns as channels, some functions take rows. You gotta just play around with it, find out what is the right output that you expect. The next thing we're going to do now is to load two sources, right? So from the same list of ambient sounds I had before, I'm going to load two sounds that I chose by their index. And using this function, I can already collapse into mono, which is what I want for my source file. And the sample rate is 48K. So I'm going to do this, and this being a mono file, you don't have to worry about channels being rows or column. This is just a single array, which dimensionality in Python does not matter too much. It can be a row, it can be a column, whatever it is. We can listen now to the original sound sources. So we have a car alarm. And we have a dog barking. So we can make this sound scene of a dog barking to a car alarm and see how it comes out. Now in the next cell, this is where all the important stuff happens. So what I'm doing here is 4 convolutions in total. Each convolution is applied using signal.fftconvolve, which is my frequency domain convolution function. The first 2 convolutions, they apply to source 0, which is the car alarm. I have to convolve the source first with the left channel of the HRIR 0, which corresponds to the front left position, and one more time with the right channel, which belongs to the right ear, of the same HRIR position, front left, and the same source. So one source, 2 convolutions. The same thing for the second source, the dog barking. We apply the left channel of the HRIR belonging to the rear right position, and then the same applied to the right channel of the HRIR belonging to that position, and we have our convolved signal for the right ear. So we end up with 4 signals. Source 0 left ear, source 0 right ear, spatialized at the front left. Source 1 left ear, source 1 right ear, spatialized at the rear right. Now, in this function, I can feed the time domain signals, but if you want to do frequency domain convolution manually, you need to use the HRTFs, which are the frequency domain version of HRIRs. And of course, you need to take the FFT of the signal as well and apply a multiplication between those two, and then take the inverse FFT. Now, the thing that we need to be careful about is how long will the signals be post-convolution. And this is important because later on we're going to add together all the left ear convolutions and add together all the right ear convolutions. So in order to add them together, everything needs to be the same length. So we're gonna check on how long these output arrays are going to be. I'm going to use the left ear as reference, but you can use the right ear, doesn't matter, it's just a way to check. All right, so we see that they are different length. So of course this is because the first source, the car alarm, is longer than the dog barking. So my final array is going to be some samples longer than the final array for the dog barking sound. You also can appreciate how fast the convolutions happen in frequency domains. So this computes pretty much instantly every time it's executed. So what are we going to do to allow ourselves to add these two together? What we can do is zero pad. So we can zero pad the smaller array to be as long as the larger array just by adding zeros at the end. So first of all, I retrieve what my target length is going to be, which is the maximum of these two signals. And then I'm going to define padding amounts. So how much should I pad one signal in respect to the other, and how much should I pad the other one in respect to its correspondent. So one of these two numbers, pad 0, pad 1, is going to be 0, while the other one is going to be the difference between one to the other. Now, if I were to have more sources, not just two, but more sources, then again, I need to find out which one is the longest one and pad each one of those to that to have the same length. Just added zeros at the end so that everything has the same number in their array length. So here I'm padding the source 0 left and right signals by the pad 0 amount, and I'm just pretending I don't know which one is longer here. So I'm padding also the source 1 signal by pad 1 amount. I think source 0 was longer, so this pad 0 is going to be equal to 0. And this pad 1 is going to be equal to the difference between these two numbers up here. And then we're going to confirm that they are indeed the same. So now we're good. Now we can add the arrays together in a straightforward operations. So I'm going to create a left ear mix, and a right ear mix. And all I got to do is add together source 0 left ear with source 1 left ear for the left mix, and add together source 0 right ear and source 1 right ear for the right mix. And these channels, these outputs, they will go directly to the headphones. Now, to put them together in a single file, I can use this mp.vstack and transpose. So now we have two columns, and they're going to be our binaural mix. So let's compute it. And now we see that the amount of samples is right as it was before. That doesn't change. And the number of channels is 2, right? The two channels being L and R. And when you add two arrays together, that basically means each cell, this is the number of cells that we have in each array. And the array cells of this one gets added with the corresponding array cells of this other one. And we mix the signals together. So we are almost ready to listen to it. First of all, I'm going to scale the amplitude. So I want the amplitude to peak at 1. I want to standardize it. This is just a safety measure to make sure that my amplitude is not too high. Otherwise, it might clip. It might clip in certain software that allow reproduction beyond the numerical value of 1, and that creates distortion. Now, this is not always the case. I think Python handles it relatively well. Just as a safety measure, I'm going to normalize. So this means I'm taking my mix and I'm dividing each value, each sample, by the maximum absolute value of the samples within the mix. And that, as a result, will scale the amplitude of everything where the highest value of the scaled version is going to be either 1 or -1. Then finally I'm going to save it, and I'm going to plot it, and this is what we get. Here we go. We have a left ear in blue and a right ear in orange. Okay, so we're finally ready to listen to our signal, our binaural mix. And remember, we had two sources. One was spatialized. The first source, which is a car alarm, was spatialized in the front left, and the dog barking was spatialized the right rear. So hopefully those are the positions we're going to perceive in this mix. Okay, so this is all. I hope everything was easy to follow, and I'll see you in part 2. Thank you very much.